So in this problem, we are going to figure out the minimum dimension. We're going to figure out dimensions of a beam that is subjected to bending as well as transverse shear stress. We need to find the dimensions that will allow this beam to survive. So we're given a certain allowable stress, so that would be an allowable tensile strength, and then we're also given allowable shear strength. And we're going to be given one of the dimensions. We need to figure out what the other dimension has to be in order to make sure that this beam will be able to support the load F. Okay, so what we have here, we're going to look for the minimum value of H that satisfies sigma allowable and tau allowable. So in other words, we need the minimum value of H that can support the force F, which is a point load at the center of this simply supported beam. And from that load F, we cannot exceed a bending stress of sigma allowable, so that's sort of like a tensile strength, and we cannot exceed a transverse shear stress of tau allowable. So this is a general rectangular beam with width B and height H. So the first thing we're going to do is, given this beam, we're going to make our free body diagram. So that way we can start looking at what stresses we have. So if we have a beam, we know that we have a force F acting at the center of the beam, and then we'll have two upward reaction loads. I'm going to call that RA and RB. And by now we've gotten enough experience with free body diagrams of this sort, so I won't go through rederiving RA and RB, but those are going to end up being both equal to F over 2. Okay, and then I guess I forgot to mention, but the numbers that we're going to use in this problem, our allowable bending stress is 50 kSI, the length of this beam is 24 inches, the force that's applied at the center of the beam is 150 kips, B, the width of the beam, will be 3 inches, and our allowable shear stress is 28 kSI. Okay, so now that we've got our free body diagram, we can go ahead and draw shear and moment diagrams, and those are what we're going to use for solving for the shear stress and the bending stress. So we're going to keep these symbolic. So our shear diagram, we will start at F over 2. We'll stay there till we hit L over 2. We come down by F, and then we'll be at negative F over 2 until we hit L. So right here we're at L over 2, here we're at L. And then our moment diagram, again, we should have plenty of practice with these at this point, but our moment diagram will look like this. So at L over 2, we will be at FL over 4. Okay, so from these diagrams we can see that our maximum Vmax, in this case both positive and negative have the same magnitude, so but our Vmax is F over 2, and our maximum moment is equal to FL over 4. So to guide our choice of H, we're going to go ahead and use the section modulus. This is a very simple application of the section modulus, but it's a handy way of guiding our design decisions for maybe more complicated beam sections. But we know that our section modulus, our required section modulus is equal to our maximum moment divided by our allowable bending stress or allowable tensile stress. And then we also know that the definition of the section modulus is that it's also equal to I over C, I being the moment of inertia and C being the distance from the neutral axis of the beam to the surface where the maximum stress is experienced. So let's go ahead and plug in some numbers here for our S required. So like we said, we know that M max is FL over 4. And remember that, so we'll go ahead and remind ourselves what the numbers are real quick. We know M max is FL over 4. So if we plug in the numbers that were given for this problem, we're going to find that M max is equal to 900,000 inch-pounds. Okay. And then, so our S required is going to be 900,000 inch-pounds over our allowable stress, which we know is 50 KSI, which is the same as 50 times 10 to the 3 PSI. So if we do this division, we'll end up with an S required, a required section modulus of 18 inches cubed. Alright, so here we can use our definition of the section modulus being that it's S equals I over C in order to figure out what our unknown H needs to be to ensure that we don't exceed the strength of the beam. The stresses don't exceed the strength of the beam. So we come back to this other equation for the section modulus. We know that S required then, given this number, will be I over C. We know that I is equal to BH cubed over 12 for a rectangular cross section. We know that C to the getting to the max stress is going to be H over 2 for a rectangular cross section. That's going to simplify to BH squared over 6, and that's equal to 18 inches cubed. Okay, so we'll rearrange this. We have H squared is equal to 6 times 18 inches cubed divided by B. And here I'm just going to plug in B directly. We know that B is equal to 3 inches, just to save ourselves a step on the screen. And then if we solve this, there's of course a positive and negative since it's a square root. Since we're caring about a physical dimension, we're going to take the positive number and we'll get that H is equal to 6 inches. Okay, so there's one thing we need to do to make sure. So 6 inches tells us that if H is equal to 6 inches, then the bending stress will not exceed sigma allowable. So in other words, the bending stress is not going to exceed the strength of the beam. The other thing we need to check though is to make sure that the transverse shear stress using this dimension H equals 6 does not exceed the shear strength, the shear allowable, or the shear strength. Okay, so now we're going to check what our shear stress is, and check to make sure that the shear stress we get using H equals 6 is lower than the tau allowable. So we know that tau max is equal to V max Q divided by IT. And if you were to calculate what Q and I are, you'll get that it simplifies, that this tau max equation simplifies to 3V divided by 2A. And that's V max, since we're looking for the maximum shear stress. A being the cross-sectional area of the beam. And then we know that V max is F over 2 from our shear diagram, and then we know the cross-sectional area is just B times H. Okay, so if we plug in all our numbers, we'll end up getting that tau max is equal to 6,250 psi. Okay, and or we can write that as 6.25 KSI. Now remember, our tau allowable was 28 KSI. So our tau allowable is greater, so the strength that we're given is greater than the stress that we induce, which means that this dimension H equals 6 inches works both for bending stress and for shear stress. So we can say that this works just fine, and the H that we want to use in this problem is 6 inches. We need an H of at least 6 inches to satisfy both the bending stress and the shear stress allowables.